Hello guys, good morning. Good morning to all of you. Let me know if everything is all right. Then we can start our session. Am I audible properly? Am I audible properly? Good morning, Harry. Okay, so in this class, we'll be talking about the collective model. So we know from the last few lectures, we are covering nuclear models. We first covered the liquid drop model. Then we went for cell model and associated things. Today we will be covering collective model, and after that another model will remain. There is Fermi gas model, and then we will switch to other topics. So what is there in this collective model? Collective, the name speaks for itself. In collective model, we do not look for any individual nucleon. Rather, we look for the combined behavior of the nucleus. Inside the nucleus, there are multiple number of nucleons. In cell model is also called single particle cell model. So where the single particle behavior is observed, but for collective model, no single particle is looked for. It is the collective thing which is looked for. So what is the need for the collective model? That is what we need to know first. So before the collective model, there are two prominent models. Firstly, the liquid drop model and the cell model. So this first part is a little bit of theoretical part that we'll just go through. We'll make you understand and we'll provide you the PDF. Liquid drop model. This model basically treats the nucleus as a homogeneous incompressible fluid drop, much like a liquid, where nucleons behave collectively. Second, it explains several phenomena like binding energy, fission, etc. quite well, and it relied on the macroscopic approach. And third, liquid drop model does not account for the discrete energy levels observed in nuclear spectra. We have told you, the nuclear also causes such discrete level spectra. So these spectra were not explained in the liquid drop model, and it also could not explain the concept of magic number, like certain nuclei having proton or neutron number or both 2, 8, 20, 52, 28, 50, 82, 126. Am I right? Good morning, Ajay. So these magic numbers were not explained in the liquid drop model that indicate particularly stable nuclei. Now in the cell model, the main thing which was concerned was the magic explanation of the magic number. What did cell model do? Cell model treats nucleons as independent particles. Independent particles moving within a mean field potential. I have already told you that the nucleons inside the nucleus create a mean field potential, and the nucleons moves independently inside the nucleus under that influence of mean field potential created by the interaction with other nucleons. This potential is modeled as harmonic oscillator on Wood section. We have already discussed about this. So we are just giving you a briefly summary of the previous two models and their limitations. So this model treats nucleons as independent particles moving in a quantized energy levels within the potential harmonic oscillator Wood section. It successfully explains the magic numbers 2, 8, 20, 28, etc. Which correspond to the particularly stable nuclei similar to the electron cells in atoms. So these many things we have already talked about, and this model predicts nuclear properties very well, particularly for spherical nuclei. For spherical nuclei, you know Q is equals to 0. So this cell model deals with the spherical nuclei very well, efficiently, but it struggles to describe deformed nuclei. Deformed nuclei means it is talking about prolate or oblate. Or collective phenomena like nuclear rotation and vibration. Nucleus also rotates, and they also show vibration. Nuclear vibration means the vibration mainly related to the surface oscillation. We'll talk about them. Many experimental results show that the electric quadrupole moments in certain nuclei are larger than what the cell model predicts. So I am giving you a table where you will see the experimental quadrupole moments are generally larger than the value which was determined from the cell model. Good morning, Molly. Now this table is quite important. This we have not discussed. You see, using the cell model, single particle quadrupole moment was evaluated, that is denoted by QSP. This QSP means Q single particle. An observed quadrupole moment Q observed. This is experimentally determined. So it was found that this Q observed is much larger than QSP, that is evaluated from the cell model. This discrepancy suggests that collective effects such as coordinated movement of nucleons are important for understanding the full structure of the nucleus. What does it say? In single particle cell model, only the last unpaired nucleon was given importance and the other nucleons were like neglected. So because of that, the evaluated quadrupole moment was found to be less than the observed quadrupole moment. So this discrepancy can be removed by considering the collective behavior, such as the coordinated movement of the nucleons. Are you getting these points? So here some of the examples of the nuclei where the observed quadrupole moment value has been found to be more than the value evaluated from the cell model. So you see oxygen 17, so it has 8 proton and 9 neutron. 9 neutron means what? You see, if it had 8 and 8 is a magic number, right? And 9, you see, you can write 8 plus 1. So it is like 8, so doubly magic. Doubly magic means if both neutron and proton number are magic numbers. So 8 doubly magic plus 1 neutron. It is talking about this 1 neutron. So you will find this neutron will decide the J value, that will come out to be 5 by 2. So here observed quadrupole moment is minus 2.6, but the single particle quadrupole moment evaluated from the single particle, it is minus 0.01, and you can see the ratio Q observed by Q single particle is 20. So observed quadrupole moment is 20 times more than the value obtained from single particle cell model. So this is a discrepancy, shows the discrepancy. Similarly for 39K, it is Z value and N value 19 and 20. So it is doubly magic minus 1 proton. Here it is 19 is like 20 minus 1. So it is doubly magic minus 1. So obviously this proton will decide the J value, that will come out to be 3 by 2. And here the observed quadrupole moment is 5.5, but the value obtained from cell model, it is 5. And as you can see here, the ratio is 1.1. So it is greater than the single particle cell model. Lutetium, here you can see Z and N. This is not closer to the magic number, it is way off than the magic number. You see, there are no closed magic number. 71 is far away from the magic number, 104 is far away from the magic number. So that is why it is characters, it said between cells, between closed cells. Between closed cells means what? Where magic number of protons or neutron exist. So 71 and 104 is much away from the magic number, so that is why it is talked about, it is between two closed cells. So for neutron, you see 175 lutetium has 104 neutrons, which is not a magic number. This means a neutral cell is not fully closed when it is equal to the magic number. Similarly, proton 71 is not a magic number either. Thus, in a region where neither proton nor the neutron cell is completely filled or closed. So for this, J value has been evaluated 7/2. So here you see it is less. Q observed by Q single particle, as you can see, it is -20. So it is, yeah, it is also greater, na? Way greater than which was evaluated by using single particle cell model. Similarly, for bismuth, it is doubly magic. 83 means 82 plus 1, and 126 is a magic number, so double magic plus 1 photon. So here spin is 9/2 minus 35 minus 30, so it is 1.1. In all of these cases, you can see the observed quadruple moment is much larger than the quadruple moment evaluated from the single particle cell model. So this discrepancy was taken care of in the collective model. Understood the basis of collective model? Now let us talk about this collective model. So we understood what were the limitations of the previous models. Now what is the basis of the collective model? It is developed by Bohr and Mottelson in 1950s, and this model was introduced to address these limitations what the liquid drop model and cell model could not explain. So you see, in liquid drop model, macroscopic idea was taken care. In cell model, microscopic approach was taken. So in collective model, it blends both the microscopic aspect of the cell model with the macroscopic approach of the liquid drop model, emphasizing the importance of collective motion of nucleons. So collective model takes the good points from both the models and give you a model. Q observed and Q SP, how they can calculate. So we talked about na QSP, we gave you the formula na, minus 2j minus 1 divided by 2 into j plus 1 into mean squared radius. We gave you na single part quadruple moment formula for cell model. So this is the SP means single particle. This is single particle. It is talking about single particle cell model, because in cell model the last unpaired nucleon decides everything, and Q observed, this is experimentally observed. Coordinated movement of nucleons means collective motion of nucleons inside the nucleus. Yes, basically is you can consider it in this way. In the cell model, only the last unpaired nucleon was observed, and the other nucleons effect was ignored. A collective or coordinated movement of nucleons means inside the nucleus all the nucleons motion is to be collectively looked at. So they move freely in a coordinated way. That thing is it is talking about. Coordinated means connected with each other. It is not like this nucleon has no influence on the others. So they will move in a coordinated way, in a collective way. We'll talk about it later on also, don't worry. Now collective motion of nucleons, here all the nucleons are considered. So mainly two aspects were not being explained in the liquid drop and cell model, that is a rotational motion and vibrational motion. So when the nucleus is rotating, it is involving all the nucleons, it is involving a collective behavior. In the same way, vibrational motion, it is mainly the surface oscillation, it also involves the collective behavior of the nucleons. So these were the thing which depends on the collective or coordinated movement of the nucleons. So this model accounts for the collective rotational motion of the nucleons, particularly in deformed nuclei. When a nucleus is non-spherical, it can rotate around different axes, leading to characteristic rotational energy levels. We'll talk about this rotational energy levels in nuclei. So this kind of rotational energy levels will be created for the nucleus. And vibrational motion, it also incorporates the idea of vibrational mode, so the nucleus oscillates between different shapes from spherical to deformed and back. It is like surface oscillation. As I will show you a picture. In this model, the nucleons inside the nucleus are no longer treated as purely independent particles, but their collective motion like rotation and vibration contributes to the overall behavior of the nucleus. So collective motion means it is rotating or it is vibrating. Okay, now try to understand very carefully what is the basic idea in collective model. You see, if I talk about the electronic configuration, we have the closed shell configuration given by 2n square, right? So when the outer shell electron is either 2, okay, 8, 18, then what is the next number? 32, na? And so on, let's say. We see that they are forming closed cell. Closed cell is said to believe that the atom is stable. Okay. The similar thing inside the nucleus, it is dealt with magic numbers. So when a particular nuclei contain this magic number 2, 8, 20, 28, 52, 126. Sorry. 50, 82, 126. So they are said to form closed cell inside the nucleus. Just check the magic number whether I have written it correctly or not. The idea of the collective model is that, let's say in a particular nuclei we have a core which contains of the magic number of nucleons, and the remaining or extra nucleons are moving outside of it in this way. So this is your core. This content magic numbers, and whatever nucleons, extra nucleons we have, they move outside of it. Now tell me, you can imagine it in this way: a core which is stable. Now some additional nucleons, they are rotating around the core. What will happen? Some centrifugal force will be applied to the extra nucleons, and if centrifugal force means what? It is some outward force. So if some outward force acts on the core, it will get deformed. The nucleus as a whole will get deformed, and that explains the deformed nuclei. Getting the point? It is like, let's say we have 70 number of nucleons. So 70 means 50 will fill up the core, and the remaining 20 will be there outside the core. So these extra nucleons or surplus nucleons will be outside the core, and they will be loosely bound. They will be loosely bound to the core. So they will apply some kind of centrifugal force and deform the nucleus. So let us write these things in words. In the collective model, a nucleus consists of a central core and some extra nucleons around the core. The core consists of a number of nucleons equal to the magic number. The loose nucleons outside the core have large centrifugal force on the core. So you see more the surplus or additional nucleons outside the core, more will be the deformation. Let's say if it is 50, so 50 will be somewhat spherical. Now if it is 55, the influence will be something. If it is 60, the influence will be more. If it is 70, the influence will be greater. And when the it is like up to 80, 81, the influence will be too much. Actually, when as you go close to 82, the influence will become less, because we are going towards the magic numbers. Okay. The loose nucleons outside the core have large centrifugal force on the core. If the number is large, they are able to deform the core. Now the total energy of the deformed nucleus will have various components. The total energy of the deformed nuclei can be written as T E. It will have three components. Firstly, energy due to the extra nucleon En plus energy due to the vibrational motion plus energy due to the rotational motion. So here EV, En, this is due to extra nucleons, EB due to vibrational motion, and ER due to rotational motion. Okay. Now, as I told you, two types of collective motion we observe. One is vibrational, another one is rotation. How do they look like? That we'll talk about. Is it done? You see, two major types of collective motion we get to see. One is the vibration, another one is rotation. So vibration basically deals with the surface oscillation. How it is carrying out? Average shape is spherical, but instantaneous shape is not. You can see in this image. This we have taken from a book. I forgot the name of the book, but it is okay. You see, it is average. You can see is spherical. So R average, you can see it is spherical, and the other shapes, you see, they are non-spherical, so it is vibrating or oscillating about this average radius. At any instant the radius is given by this, at any angle theta phi. So different vibrational modes exist. For rotation of a deformed shape, so which deviates from the magic numbers, it will be deformed. So you can see it is which structure? Can you tell me? Can anyone tell me what kind of structure it is? It is prolate or oblate? It is prolate or oblate. So energy of a rotation or rigid rotation is given by r square by 2I. R is the rotational operator. It is oblate, but symmetry axis is this, na? This is your z axis. It should be oblate or prolate. Symmetry axis is this. So how did you consider? We took the z axis or symmetry axis, and with respect to that, if it is elongate along the symmetric axis, that is prolate, and if it is in the perpendicular direction, we call it oblate. Here you can see this is a symmetry axis, na? So it should not be prolate. Rotation prolate, yeah. For vibration we don't consider, that's for this one prolate. Now you see h rotational is equals to r square by 2I. H is the energy operator. Now if we try to solve this, we can use the formula h psi is equals to E psi, right? You know, this is from quantum mechanics. We say h psi is equals to E psi. So let us write it in this form: h rotational of psi is equals to E psi. This is your Schrodinger equation, although we have not discussed quantum mechanics yet, but you know it. This is Schrodinger equation, so we can solve this Schrodinger equation. H rotational is this. Let's take that. R square by 2I applied on psi. E equals to, let's say, Ej of psi. So we write it r square y j m, this is equals to j into j plus 1 h cut square y j m. So from this we get Ej is equals to h cut square by 2I times j into j plus 1. So mainly you need to remember this formula, okay? You can ignore the derivation. This one you need to know. This is the rotational energy levels, like this: j goes to 0, j goes to 2, j goes to 4, and so on. So this gives you the rotational energy levels. Now from this we get the value of j's to be 0, 1, 2, 3, 4, and so on. What is surface oscillation? It is like you imagine something which is able to deform. Consider a polythene bag, and you have filled with water. Okay, not completely filled. It is like filled, which can be deformed in different shape. So it is like let's say once it is spherical, then it is like rugby ball, then it is like this. So you can imagine it in this way, this figure. Imagine polythene filled with water. So it is maintaining the average spherical shape, but it is also making this kind of shape, elliptical and this ellipsoidal. Actually in 3D it is ellipsoidal and this kind of shape. So this is termed as surface oscillations. The surface is not maintaining its shape. The surface is oscillating and making different kind of shape. So it is shape oscillations. Vibration, it gives oblate. No. For rotation, we will consider this oblate or prolate. For vibration, we do not consider this, whether it is oblate or prolate. You consider for this is not related. Actually I have just asked you what kind of structure it is, prolate or oblate, because it should be rigid. Otherwise how will you say prolate or oblate? It is constantly vibrating, so we do not have a fixed shape, so we cannot distinguish prolate or oblate. A rotational rigid nuclei, rigid rotator, actually we can say it is prolate or oblate. For vibration we cannot say. So yes, actually I had a dissertation paper on this nuclear physics, so I know there exists some vibrator nuclei and there exists some rotor nuclei. These are called rotor nuclei. So I have also dealt with some experimental results on the what are the nucleus which act as vibrator nuclei, and which nuclei acts as rotor nuclei. So this prolate and oblate structure you will get to see in the rotor nuclei, not in vibrator. Clear? Everything is all clear? Now you can see, as I told you, here from this calculation we are getting j equals to 0, 1, 2, 3, 4. Now all the j values are not allowed for rotor nuclei. You see, parity needs to be taken into consideration. Parity is equals to minus 1 to the power j. J is the spin, but there is a reflection symmetry, so odd j is not acceptable. Odd j is not acceptable because of the reflection symmetry. Allowed values of j are 0 to 4, etc. So you see, for rotational system, parity is minus 1 to the power j. When a system has reflection symmetry, certain parity constants are imposed. So to explain this reflection symmetry, I have added these 2 points. Firstly, if the system's parity is even, only even of values of j will be allowed, and minus 1 to the power j must be positive for reflection symmetry. So only even value of j can give you minus 1 to the power j equals to positive or plus 1, which happens when j equals to 0 to 4. Odd values of j such as 1, 3, 5, if you take odd value of j 1, 3, 5 and so on, you see it will always give you minus 1. So that violates this reflection symmetry, would result in negative parity, which is not acceptable for a system with reflection symmetry. Thus, due to this symmetry, only even rotational quantum numbers are allowed, and the allowed values are j is equals to 0 to 4. So your modified formula is Ej is equals to h cut square by 2I into j plus 1. where the allowed values of J are 0, 2, 4, 6, 8 and so on. So you need to remember this formula for rotational nuclei. Don't take J equals to 1 or 3. So many people make mistakes on this. So one example of rotonuclei, you can say uranium-238. I am giving one example of uranium-238. You see, as the allowed values are E0, 0, 2, 4, 6 and all of them parity is -1 to the power j. If you take j to be even, -1 to the power j will always come out to be plus. So that is why we get 0 plus, 2 plus, 4 plus, 6 plus, 8 plus. Now, even values of spin 0, 2, 4, 6, 8. So these are the j value. J equals to 0 here, j equals to 2 here, j is equals to 4 here, j is equals to 6 here and j is equals to 8 here. Now what is the ground state energy? Ground state energy E0 is equals to 0 है ना. Look, we have this original relation Ej is equals to h cut square, sorry, h cut square by 2i times j into j plus 1. J goes from 0 to 4, 6, 8 and so on. So ground state energy will be E0 is equals to 0. What about the first excited state? First excited state energy, you see we have taken j equals to 0, so we have to take j equals to 2. So first excited state will be E2, not E1. E2 will be h cut square by 2i, 2 into 2 plus 1. So this is 6 times h cut square by 2i. From this we can get the value of h cut square by 2i. This is equals to E2 by 6. So this value of h cut square by 2i will be used many times. So that is why we have calculated the value of h cut square by 2i separately. Now the remaining we can express, and as a result we can formulate a general formula of Ej. Ej is equals to, you see, h cut square by 2i into j plus 1. So we can write 1 by 6 j into j plus 1 E2. So where j is equals to 0, 2, 4 and so on. This one we wrote in terms of first excited state. First excited state energy E2. Should it follow reflection system for deformed nuclei? Yes, Murli. Actually, rotating nuclei, that will be, those are deformed nuclei. Rotor nuclei, they are deformed nuclei. The deformation is coming from the rotation only, na? Imagine these nucleons are deforming the core. It is originating from the rotation itself. Everything is well connected. Clear? Let me give you a question. So try to solve this problem. This came in December 2017. The first excited state of a rotational spectrum of the nucleus 92 uranium 238 has an energy 40 kilo electron volt above the ground state. The energy of the second excited state in kilo electron volt is. So you see, this is the ground state. As you go on, the separation between the levels are increasing. This is your first excited state, second excited state, and so on. This is E0, E2, E4. First excited state of rotational system has an energy 40 kilo electron volt above the ground state. So this much of energy is 45 kilo electron volt. The energy of the second excited state. So this is first excited, this is second excited state in kilo electron. So E4 we need to remember, we need to determine. Give it a try. Look here, one addition, this is not, well, this is an information used here. You see, this information that R square while applying on yjm produces j into j plus 1 h cut square. This thing we have put here to evaluate this value. Okay, so R square psi is like j into j plus 1 h cut square psi, and from that we get this relation. I hope this is clear now. You did not ask, but let me tell you. Option A you are getting? Yes, option A will be the answer. So you see how to solve this. 45 kV, this is E2. E2 is equals to h cut square by 2i into j plus 1. So 2 into 2 plus 1. So from this we can evaluate the value of h cut square by 2i. So h cut square by 2i is 45 by 6 keV. So we need to find out E4. E4 is equals to h cut square by 2i, 4 into 4 plus 1. So 45 by 6 into 20 keV. Is it okay? 900 by 6 keV, 150 keV. Yes, Harry, Murli, Ajay. Chalo, let's do another problem. So from this model, generally this type of question comes very easy, but the conceptual part is important for interview. That is why we have spent some time in the conceptual part. Otherwise I could have given you just this formula and you could have easily solved the problem, but the concept is important, guys. The first three energy levels of 90 thorium 228 are shown below. The expected spin parity and energy of the next level. So you find the closest one. It may not come exactly, but you can find the closest one. Quickly do. Option A, very good. So obviously the next level will be 6 plus, and the spin parity we can easily say it is 6 plus. Energy of the next level. Energy means we need to find out E6. So E6, if you want to know, already we know E4. So E6 is equals to h cut square by 2i into 6 into 6 plus 1, and let's say E4. E4 is h cut square by 2i, 4 into 4 plus 1. No, this is given to you 187 keV. So if I take, let's say, the ratio of E6 and E4, we should get 6 into 6 plus 1 divided by 4 into 4 plus 1. That gives you E6 is equals to how much? (42 by 20) times E4. E4 we already know 187 electron volt. So 42 by 20 into 187 electron volt. So what it is coming? Let's try to evaluate. 42 into 187 divided by syntax. (392.7). 402 कैसा है क्या? It is 392.7 keV. So which we can approximate with 400 keV. Check the calculation, it will come out to be 393 approx. Everybody got 393? Harry, Murli, Ajay? Can you move on? Yes, Harry. Now, one question I would like to give. This came in December 2018. The low lying energy levels due to the vibrational excitations of an even nucleus shown in the figure. The spin parity Jp of the level E1 is. I think without actually knowing the solution, you can tell me the answer. D. Will be 2 plus. Okay, so when change in spin is 2, what kind of phonon is that? It is quadruple, na? When the change in 2 unit is quadruple. You see, it is delta E. So change in the spin, it shows you one. It is due to one quadruple phonon. Here, look, this is not like only 2 plus is having approximately 2 delta. You can see the energy level 1.17, 1.25, 1.35. So they are basically similar type of energy level. So it is 2 times delta E. So it involves 2 quadruple phonons, 2 identical quadruple phonons, because you see, it is, you can consider it not only 2 plus, it is like the whole, this whole level is roughly around 2 delta E. So if this involves 1 quadruple phonon, this involves 2 quadruple phonons. Two quadruple phonons, 1 quadruple phonon, and 2 quadruple phonons means what? 1 octupole. But this is an extra information. What we know is the spin parity of Jp of the E1 level will be 2 plus. That is the answer. So you see, from nuclear physics, very easy questions come. So that is why this is very important. It will save your time during the examination, and it will give you good good number of marks also. with accuracy. That is why we definitely should cover nuclear physics. Now, okay, let me just give you brief introduction about the Fermi gas model, then we'll continue it from the next day. So, this is the last model which we will be talking about, last nuclear models. This is, the previous models which we discussed was strongly independent or strongly interacting fermions. But this is another type, no, Fermi gas model. The Fermi gas model explains the nucleus as a system of weakly interacting fermions, proton or neutron, that move freely inside the nucleus. Nucleons are treated as fermions obeying Pauli's exclusion principle and occupying discrete energy levels inside a binding potential. So, as you can see in this figure, that there exist separate walls for protons and separate wall for neutrons. Now, protons and neutrons both are spin half particles. So, in one energy level, there will be only two species, two protons. Here you can see two neutrons, two protons, two neutrons. And the potential wall is roughly rectangular, but it is shows some this curve type thing at the edges. The potential wells for protons and neutrons are shaped as rectangular wells. Neutrons and protons occupy states up to their respective Fermi energy EF. So the highest occupied energy level, you can see this is EFP, Fermi energy for proton. This is the EFP, and this is also EFN, Fermi energy for neutron. You see the neutron's well is deeper as compared to the proton's well. As you can see, this is deeper, but the Fermi level is same for both of them. Proton potential, two separate potential well, as I have talked about. So, okay, let me just show you. This is your proton well and this is your neutrons well. So their depth of the potential for both of them are different. Proton potential, proton energy level form a well with a different depth from neutron due to the additional effect of Coulomb forces. Proton involves electrostatic repulsion, because of that it has less depth potential well. Neutron potential deeper well for neutron because they are unaffected by the Coulomb forces. Now, although you see spin half means what? Total multiplicity is 2s plus 1. So 2 into half plus 1 is equals to 2. So one is spin up, another one is spin 2. In this way it is arranged. So each nucleon, proton or neutron, has two spin projection. It may be up and down. So each energy level can hold two particles. Particle field energy level is starting from the lowest up to a maximum energy known as the Fermi energy. Fermi energy, you know already the definition, that the highest energy of the highest occupied level is the Fermi energy. All available energy states are filled by the pairs of nucleons. Hence, there are no free states and consequently there are no transition between the states. What does it say? As you can see, the levels are all filled with nucleons. It may be either by protons or by neutrons. So there is no excess level where these protons or neutrons can go. So that is why there is no transition involved. There are no free states and consequently there are no transition between the states. Now, as you can see, what happens to my thought? Now carefully look at, this is the Fermi energy level. This is the this is the Fermi energy level, as you can see in the along this line. This is EFP, EFN, and this is the top of the potential well. So this Fermi energy level and the top of the potential well has some difference, that is denoted by B prime. The difference B prime between the top of the well and the Fermi level is constant for most nuclei, and it is just the binding energy per nucleon, 7 to 8 MeV, and that is quite obvious now. This, because of this gap of energy, the nucleons, proton and neutrons could be bound inside the nucleus. So if you give this much of energy, they will have sufficient energy to leave this potential well. Okay, so we'll discuss about this Fermi gas model in detail on the next day. We'll review this one once again, and here we end the session today. So in this lecture we have covered the collective model, and the next lecture will be covering Fermi gas model, and after that we can go for nuclear reaction. Is there any question you can ask? Otherwise, let's end the session here today. Thank you very much for joining the session. I hope you find the session useful, and have a great day. Bye bye. Take care. See you in the next class.